Okay, now we start the congruence and simultaneously diagonalization of Hermitian and symmetric matrices. And when Professor Roger Horn visited Seongkyungan University, he talked about the star congruent and T congruent. Yeah, this is that part. Let A and B are n by n complex matrix, and there exists a non-singular matrix S such that if B is equal to S star, then we say B is star congruent to A. Okay? Star congruent. If B is equal to S transpose, then we call B is T congruent to A. Okay? This is a generalization of the similarity that you have learned. When A is a Hermitian matrix, you have real eigenvalues. Now we define the inertia of A. Inertia of A. I of A. This is the set of three numbers. The first part, I plus of A. That is the number of positive eigenvalues of A. It is also called the index of A. Number of positive eigenvalues. I plus of A. Okay. Next, I minus of A is the number of negative eigenvalues of A. Okay. I minus of A. And the last, I zero of A is the number of zero eigenvalues of A. So inertia of A is the set of these three numbers. And also, the signature of A is the difference between number of positive eigenvalues and the number of negative eigenvalues. And the rank of A is the addition, rank of A is the number of all non-negative eigenvalues. So it is the addition of I plus of 1 and I minus, I plus of A and I minus of A. Let's say if this is R and this is P, then what is this? What is this? Okay, then this is T, then R plus T is equal to P. No. P plus T is equal to R. Then T is equal to R minus P. Then what is signature? This is P minus T. T is this, R minus P. So what is this? 2P minus R, like this. So it has some relationship like this. Okay? Anyway. So yeah, you just remember, inertia is this. The vector of three numbers. Very important. Inertia. Okay? Let sigma, the set of eigenvalues of A are in this order. And D is a diagonal matrix with this. Then sigma, gamma, can be written in this way, where A is equal to U delta U sigma. Here, identity matrix and minus identity matrix and zero matrices, like this. So, the matrix A, if it's written in U gamma U star, then this can be written in this way. We say this is the inertia matrix of A. What this means is we know here we know the positive eigenvalues. We know the number of positive eigenvalues there, isn't it? Then how many of that? We have P. So we have 1, 1, 1 here is P by P. Okay, here. And here we have minus 1, and minus 1. What's the size of this? R minus P, isn't it? R minus P. And the others are zeros, like this. Okay? So we call that the inertia matrix. If we have a if we know the inertia, I of A, then we can make the inertia matrix I of A, isn't it? We know the number, then we can just make the inertia matrix. Okay, this is the Sylvester's law of inertia, which was proved in 1852. If A be a Hermitian matrix, and if there exists a non-singular matrix S such that A is equal to SB S star, if they are star congruent, then A and B has same inertia. It has same index, it has the same signature, and same length, isn't it? Okay, cool. This theorem states that Hermitian matrix is star congruent to exactly one diagonal matrix like this, with the diagonal entries all being +1, -1, or 0. This is what the Sylvester's law of inertia says. If a Hermitian matrix is star congruent, then it is star congruent to exactly one diagonal matrix, which is inertia matrix of A, isn't it? This is what Sylvester's law of inertia says. I will show the proof in detail because you better know. Okay. Suppose it has A and B has the same inertia. Suppose they both has the same inertia. Then A can be written in this way and B can be written in this way for some invertible matrix S1 and S2. Okay? Yeah. It has the same inertia matrix. Same inertia matrix because it has same inertia. Then we just write it. That I of A, this is non-singular, so I of A can be written in this way. And this is same as this. And this we can write, this is one non-singular matrix S. Then you can write it as SB, S star. Then A and B are star congruent, isn't it? Okay. So it has the same. So there's a non-singular matrix S. Let S is equal to S1 S inverse, S2 inverse. Done. Next. Suppose there exists a non-singular matrix S such that A is equal to SB S star. Then we show A and B has the same inertia. Okay. First, there is a non-singular matrix S such that this. So what? Rank of A and rank of B are same. What this says is it has the same number of non-zero eigenvalues, zero eigenvalues and non-zero eigenvalues. So we know this. So all we have to show is if we know the number of positive eigenvalues are same, then since lengths are same, we know it has the same number of negative eigenvalues. Then we have the same zero eigenvalues, same number of zero eigenvalues. We have the same number of positive eigenvalues. Then we have the same number of negative eigenvalues. So the proof is done. So all we have to do is this. All we have to show it has the same positive eigenvalues. Okay. Now we start. Let V1 and V2 and I plus of A be the orthonormal eigenvectors of A corresponding to the positive eigenvalues of A's. Okay, we have that many number of positive eigenvalues of A. Okay, so it has. We can find the eigenvectors, and also we can find the orthonormal eigenvectors. And then let S plus of A be the span of these eigenvectors. Span of it. Then the dimension of this is same as number of positive eigenvalues. Okay? Because they are linearly independent. Okay, so here, if X is equal, if let X be a linear combination of those VI's, then X star AX can be written in this way. Because those X, and then those X can be written in this way, and these V's are also normal. So all gone. Closing terms are all gone, and the eigenvalues are left. But as you see, these are all positive eigenvalues, and these are non-negatives. Okay. So positive eigenvalues, and some of this, and also this is a non-zero vector. So some of alpha i's are non-zero. So these are all positive. These are all positive, and some of these are positive. So we should have a positive. So this X star AX is positive. Okay, what that gives us is this. What that gives us is, think about this. Think about X star SBS star X, which is this. This is positive because that was A. That was A. So this is positive, you know it. Here, let's write it. That was vector Y. Replace the S star X as Y. But this Y is in the span of these vectors. Span of those vectors. And this is true for all Y, all non-zero Y in this subspace. What's the dimension? What's the dimension of this? This is I lost one is one. This B1 B1 is okay. Yeah. Okay. Here. So what's the dimension? So what this means is for any non-zero vector Y, this is positive. That means the dimension is not less. The dimension of this space, this space is not less than the dimension of those axes, the set of these axes, which comes from here. So what this says is, if anything are positive, what that says is the dimension of this space is not bigger than or equal to the dimension of this, which says the index of B is not smaller than the index of A. Okay. Similarly, we can start with the B, and then we can show for the A's to get the other direction of inequalities. Combining these two, we have the equality for the index of A and B. Then we have the equality for the negatives, which which gives us the same inertia for the matrix A and B. So it concludes the other part. So now we have, for two Hermitian matrices, if it's star congruent, then it has the same inertia. That's what Sylvester showed in 1852. Okay, that's called the Sylvester's law of inertia. Okay. If we write it in other way, then suppose we have a Hermitian matrix of size n, then Sylvester's law of inertia says H is star congruent to such a matrix like this, whose shape is IP, the direct sum of these three matrices. Zero matrix, it's a zero matrix. When R is a rank of H, then M minus R is the size of nullity. So we have zero matrix here. We have identity matrix, which has index size, and the minus identity matrix, whose size is R minus P. Okay. So star congruent preserve the signatures. Okay. But you should know, but star congruent can make the change of the eigenvalues. The size of eigenvalues can be changed. It only says about the number of the positive and negative and zero eigenvalues. We can always make the changes on the size of the eigenvalues. Okay, so the Ostrowski theorem shows what can be happened to the size of the eigenvalues. You can do some problems here. And the book says, see the table on page 229 at the end of the chapter 4. And this is that table here. Some relationships and similarity and conjugate transpose and star congruent and transpose and T congruence and the property equivalent statement and things. So just take a look. This is page 229. And there are some homework problems on this chapter and section, page 251. And I assign you 3 problems. And Jin, Sung-tae do first number 1 problem, and Hana do the problem number 9, and Horor and Jung do the problem 12. I think this is the end of chapter 4, which was a long chapter. Any questions on chapter 4? Any questions?